Chemistry 101, Practice Exam 4. Question number 1. Which of the following is a true statement concerning the specific heat of a substance? Specific heat, we use the variable C, or sometimes we use SH. And you would remember that the units for specific heat are calories per gram degree Celsius. So let's take a look at the possible answers. The first one is specific heat is the amount of heat that's required to raise 1 gram of a substance by 1 degree Celsius. Well, based on the units for specific heat, this is the correct answer. B, specific heat is the change in the temperature of a substance as it absorbs heat. Of course not. That's not specific heat. That's just a change in temperature. Specific heat is the heat given off in a chemical reaction. No, that's not specific heat. Specific heat is 1 calorie. Well, for water, it's 1.00 calories per gram degree Celsius, but definitely not for all substances. And specific heat is the amount of heat to raise 1 mole of a substance by 10 degrees. Definitely not. So there we go. That's the answer to number 1 is A. Moving on to number 2. What is the name and symbol of the thermodynamic quantity that represents the heat absorbed or liberated in a chemical reaction at constant pressure? That's a definition that you should be well aware of, and the variable that fits that definition is delta H, the change in enthalpy. And the change in enthalpy is defined as the heat that is absorbed or liberated in a chemical reaction at constant pressure. Question number 3. Which of the following represents an exothermic reaction? The way you can think about this is exo is leaving or exiting, and thermic is going to be heat, energy. So heat or energy is going to be a product. And if I take a look at the first reaction, I'm taking A and I'm converting it into B, and I also end up with energy as a product. So since energy is leaving or exiting, this is going to be an exothermic reaction. And of course, when you're dealing with an exothermic reaction, the change in enthalpy is going to be a negative number. Now, if I look at B, you can see that the delta H is a positive number. Therefore, that is not an exothermic reaction. And if you look at C, in C, you have to put in energy in order to get the reaction to occur, to convert the 2 moles of A to C into D. So therefore, C is not a possible answer. Question number 4. When a sample of aqueous hydrochloric acid, that's HCl, was neutralized with aqueous sodium hydroxide, therefore this is an acid-base problem or neutralization. So when you mix hydrochloric acid with aqueous sodium hydroxide in a calorimeter, the temperature of 100 grams of water surrounding the reaction increased from 25 degrees Celsius to 31.5 degrees Celsius. If the specific heat of water is 1.00 calories per gram degree Celsius, calculate the quantity of energy in calories involved in this neutralization reaction. Now, we're given the mass of our water, which is 100 grams. We can calculate the delta T, which is 31.5 degrees Celsius. Subtract 25 degrees Celsius. Remember that delta T is always the final temperature. Subtract the initial temperature, and that gives us a delta T of 6.5 degrees Celsius, 2 sig figs there. And then I also have my specific heat of water, which is 1.00 calories per gram degree Celsius. Now, in order to figure out the quantity of energy involved in this neutralization reaction, I'm going to use the formula Q is equal to MCAT, or Q is equal to MC times delta T. I'm going to plug in my numbers. So I have my mass, which is 100.0 grams. I have my specific heat of water, and I have my delta T, which is 6.5 degrees Celsius. You can see that the units of mass and temperature cancel out, and I end up with a Q that is 650 calories, and there we go. Question number 5. Which of the following is a process with a negative delta S? And you would remember that S is entropy, and entropy is a measure of randomness, or disorder is another way you could think about it. So if I have a positive delta S, that means I'm increasing in disorder. And if I have a negative delta S, this means that disorder is decreasing. Another way we could frame that is to say order is increasing. So something is getting more ordered. Okay? And if I take a look at the possible answers, in A, I'm going from water in the liquid phase to the solid phase. What do we know? That when we take water in the liquid phase and we convert it to the solid phase, when we make ice, the water is crystallizing and it is becoming more ordered in that crystalline phase, or that crystalline state rather, in the solid state. Therefore, A must be the correct answer. If we take a look at the other possibilities, if I go from a solid to a gas, well, in a solid, carbon dioxide solid, the particles are going to be much closer and much more organized than in the gas phase, because gases are mostly empty space and the particles are going to be moving much faster. Therefore, a gas is going to be more disordered, so I would have a positive delta S in that case. In C, I'm going from calcium carbonate solid to calcium oxide solid and carbon dioxide, so I'm going from one reactant and I'm making two products. So I'm going from one substance to two substances, and therefore I'm increasing the disorder. The next one says dissolving sugar in water. So if we said, okay, well, if I have sugar, which is glucose, there are many sugars, but if I take glucose and I dissolve it in water, what am I doing? I'm taking solid glucose and I'm basically making an aqueous solution of it. So what am I doing? I'm taking those sugar particles, the molecules that are closely packed together in the solid phase, and when I have them in the aqueous phase, the particles are going to be dispersed from each other. They're going to be farther apart in that aqueous solution. Therefore, that would be an increase in disorder. All right, so the answer for number 5 is A. Question number 6, under normal conditions, which of the following would have the highest entropy? And again, in the same vein of question 5, highest entropy, we could say most disordered. Most disordered. You know, sometimes I like to think, or I don't like to think about it, but when I walk into a messy room, you know, if I go into my kids' bedrooms and it's a big mess, I'll think entropy, you know, just disorder. So that's the way you could think about entropy, just disordered. So under normal conditions, which of the following would have the highest entropy? I've got liquid water, solid sodium chloride, ice, solid iron, and steam. I'm going to cross out all the solids because those are going to be ordered, right? Ice is a solid, and of course the other two, solid sodium chloride and solid iron. What do we know about solids? The particles are going to be close together. There's going to be very little movement at the atomic level. Now, if I compare liquid water and steam, steam is water in the gas phase. Well, both of them are the same molecule, water and water. Which one is going to be more disordered? Steam, right? Because if it's a gas, the particles are going to be farther apart, more spread out, and they're going to be more random than they would be in the liquid phase. Number 7, a reaction will be spontaneous at all temperatures under which conditions? And you would remember that in order for a reaction to be spontaneous, okay, I'm just going to draw an arrow down here, well, you can use the formula that the change in Gibbs free energy is going to be equal to delta H, the change in enthalpy, minus T delta S. And in order for the reaction to be spontaneous, delta G must be negative. Delta G's got to be negative. Well, how could I ensure that delta G is negative? The only way to be sure that delta G will always be negative, no matter what the values for delta H, delta S, and delta T are, is like so. In order for delta H to be a negative number, and then subtract, and then my T is in Kelvin, therefore it's always going to be a positive number. So if I take a negative number and I subtract a positive number, I'm always going to have a negative number. My delta G will always be negative, and therefore the reaction will always be spontaneous. So if T is positive, that would mean that delta S has to be positive as well. So I would subtract a positive number. Therefore, in that case, the delta, in order for the delta G, let's write it like this, for delta G to be negative, delta H has to be negative, and delta S has to be positive. And this is every scenario, okay? In order for delta G to always be negative, no exceptions, delta H must be negative. Now, what do we know about that? That's called an exothermic reaction. Exothermic reaction, or exothermic. And in order for delta S to be positive, this must be an increase in disorder. Well, let's take a look at the possible answers. D, it says the reaction must be exothermic, and accompanied by an increase in disorder, So the answer is D. Question number 8, which of the following is always necessary for a reaction to occur between two reactants, A and B? So if I have A and B and I'm combining them and I want to get some kind of product, maybe it's C, maybe it's D, I'll just write the word product. It says A and B must be present in the same physical state. So that means they both must be gases or they both must be solids. Well, that's not necessarily true. If you've ever seen the reaction between sodium, which is a solid, and water, which is a liquid, you know that's a very violent reaction. So this cannot be true. The next one, the reaction must be carried out at room temperature. Well, that's not true. Many reactions occur at temperatures other than room temperature. There must be equal amounts of A and B present. Well, that's not true. We looked at enough stoichiometry to know that maybe the reaction, maybe you need 2 moles of A and maybe you need 3 moles of B. Who knows? And then the next one says the reaction must be carried out at a higher temperature than room temperature. Also not necessarily true. We can run many reactions at low temperature. But look at the last one. It says A and B must collide with sufficient energy and the proper orientation. This is true. In order for a reaction to occur between those two reactants, yes, they have to collide with sufficient energy to overcome that activation energy, and they also have to collide with the proper orientation. Question number 9. Which of the following actions can alter the activation energy of a reaction? And if we think about a reaction, let's take a look at an exothermic reaction here. Here's energy, and this is our reaction coordinate. So if you think about activation energy is this, this hump that we have to get over here. And it says here, which one of these can alter the activation energy? Changing the temperature will not affect the activation energy. Changing the concentration of reactants, well, that won't affect the mechanism of reaction, so that's not going to change the activation energy. Changing the concentration of products for the same reason as B, it won't have any effect. Changing the size of the reaction vessel, if it were only that easy. But if I look at E, the effect of adding a catalyst, what adding a catalyst does is it changes the activation energy. So sometimes for the effect of adding a catalyst, we'll draw our reaction as occurring like this, so that the activation energy is lowered like this. So this is the effect of a catalyst, is that it lowers the activation energy. Therefore, the answer is E. Number 10, in kinetics, the order of reaction can be deduced from a balanced equation for the reaction, depends on the rate constant, depends on the concentration of the reactants, must be determined experimentally, and is the inverse of the entropy of the system. Well, let's say we had a reaction that had something like A plus B gives you C. The way that you would write the rate law for that reaction would be rate is equal to K times the concentration of A to some kind of exponent and B to some kind of exponent. And the only way to determine these exponents, the order of reaction, is to do it experimentally. So we could write that down. We would say exponents, or the order of reaction, we'll just say order of reaction, let's keep it simple, must be determined experimentally. Now, in Chemistry 101, we don't look at problems that involve determining the order of reaction with respect to each reactant. But if any of you are interested in taking Chemistry 112, which is General Chemistry 2, you would actually learn how to determine the order of reaction with respect to the reactants and determine a rate law. Question number 11. The rate of a chemical reaction increases with an increase in temperature. Which of the following correctly explains why? Let's take a look at all the possibilities. At higher temperatures, more reactant molecules are present and collisions occur more frequently. That makes no sense whatsoever. How would I increase the number of molecules just by increasing the temperature? The number of molecules in a reaction isn't going to change, isn't going to be affected just by changing the temperature, so this is impossible. At higher temperatures, the activation energy is increased. In C, it says at higher temperatures, the activation energy is decreased. Changing the temperature is not going to have any effect on the activation energy. Won't change anything. At higher temperatures, a catalyst is usually present. Well, a catalyst being present, that just means that the experimenter added the catalyst to the reaction. You can't form a catalyst by increasing the temperature, so that's impossible. Let's take a look at E. It says at higher temperatures, reactant molecules, they move faster, right? They have more kinetic energy. And if they're moving faster, that means there's going to be more collisions and more effective collisions, right? Because not only do molecules have to collide with each other, they have to collide with sufficient energy, and we saw that in an earlier problem. Therefore, E is the correct answer. At higher temperatures, the reactant molecules are going to be moving faster, they're going to have more collisions, and therefore more effective collisions that will affect the reaction. Number 12, which of the following is false about the energy diagram shown? Well, let's first take a look at the delta H. It says that the delta H of my reaction, of this reaction, is negative 50 kilojoules. And if I look at the formula for delta H, it's going to be the enthalpy of the products minus the enthalpy of the reactants. I'll just kind of do a shorthand version here. If I look at the enthalpy of my products, it's 25, and the units are kilojoules. And then I look at the enthalpy of my reactants. So this is my product, the 3, and then the 1. This is my reactants. Subtract 75 kilojoules. 25 subtract 75 gives you negative 50 kilojoules. So this one seems legit. The activation energy is 100 kilojoules. Now, the activation energy is the barrier that the starting material or the reactant has to get over. Okay, this is my activation energy to cross this high point here, the transition state. And you can see that the activation energy, the distance from this point to this point is from 100 to 75. Therefore, the activation energy is 25 kilojoules. Therefore, this answer is false. So that is the correct answer. It says here 0.2 represents an activated complex. That is true. The reaction is exothermic. Yes, if I have a negative sign for my delta H, this is exothermic. And the energy of the products is lower than the energy of the reactants. Well, if energy is increasing, going from 25 to 50 to 75, yes, the energy of my products is lower than those of my reactants. Question 13, the reaction A plus 2B plus C gives you D and 2 moles of E is first order with respect to reactant A. Let's underline that. First order in A, first order in B, and second order in C. What is the rate law for this reaction? If I just write down a simple reaction here, if I say that my rate is equal to K, this has got nothing to do with this problem. But if I say it's A to the X, the X, this is the reaction or the order. Let me erase that. This X, this is the order. X is the order with respect to this reactant. Okay, so with that in mind, let's write out our rate equation. So it's going to be that rate is equal to a rate constant, K, multiplied by the concentration of A. We're told that it's first order. If it's first order, my x, or my exponent, will be 1, so I leave that out. And it's first order with respect to B, and it's second order with respect to C. There we go, and this is my rate equation. Question 14. Consider the reversible reaction. Nitrogen plus 3 moles of hydrogen produces 2 moles of ammonia. What is the correct expression for the equilibrium constant for this reaction? This is just a matter of learning how to write equilibrium constant expressions for our reactions. You can see that our reactants and the product are all in the gaseous phase, so we're going to include all of them in our equilibrium expression because we leave out pure liquids and pure solids. And our K equilibrium is going to be equal to the concentration of our products. Now in this case we've only got one, which is ammonia, to the power of its stoichiometric coefficient, which is 2, divided by the concentration of our reactants. So the first reactant is nitrogen, to the power of its stoichiometric coefficient. It's a 1, so we put nothing for the exponent, and then times the concentration of hydrogen, and its stoichiometric coefficient is 3. There we go. That's our equilibrium expression, which is this one right here. The next question, what is the equilibrium constant for the expression? What is the equilibrium constant expression for the reaction shown below? Remember, in our equilibrium constant expression, we leave out pure liquids and pure solids. Pure solids. Solids. We leave those out of the expression. And then if I examine what I've got in my reaction, I'm taking magnesium carbonate, which is a solid, and it's in equilibrium with magnesium oxide, which is a solid, and carbon dioxide gas. Therefore, the only thing that I can include in my equilibrium constant expression is carbon dioxide. And if you're wondering, do I leave both of these out? The answer is yes, because they're both solids. So they're not going to be included in the equilibrium expression. Therefore, our K equilibrium is going to be equal to the concentration of the product, the only product that we're concerned with, which is carbon dioxide, because it's a gas. Its stoichiometric coefficient is 1. Therefore, that is my K equilibrium constant expression, which is D. Question 16. A reversible reaction is said to have reached equilibrium when each of the following conditions is established. I've gone ahead and written the reversible reaction arrows. A says the reverse reaction begins to occur. B, the reactants are completely consumed. C, the concentration of reactants and products become equal. D, the rate of the forward and the reverse reaction become equal. That is the definition of when a reaction is reached equilibrium. And then E, the rate of the forward reaction diminishes to 0. So the answer for this one is D. I would say this one is kind of a definition that you need to be aware of, that a reversible reaction is said to reach equilibrium when the rate of the forward and the rate of the reverse reactions are equal to each other. Question number 17. In the industrial synthesis of ammonia, the equilibrium constant expression may be written as follows. Calculate the value of this equilibrium constant. So we're looking to calculate our KEQ if the equilibrium concentration of nitrogen at 600 degrees Celsius is 4.53 molar, hydrogen is 2.49 molar, and ammonia is 7.62 molar. This is nothing more than plugging the numbers into our formula, which is right here. So I'm going to plug my numbers in. The concentration of my ammonia is 7.62 molar, and I'm going to square that divided by the concentration of my nitrogen, which is 4.53, and then I'm going to cube the concentration of my hydrogen, which is 2.49 cubed. I did the math on this already. You end up with 58.1 in your numerator divided by 69.9 in your denominator, which equals 0.831. I'm off by a little bit, but close enough to see that the answer is B. Number 18, for a reaction where A in the gaseous phase is being converted into 2 moles of B, I'm given my K equilibrium. Which statement is true for the system at equilibrium? Well, look, I'm given a reaction, beautiful reaction, and I'm given an equilibrium constant. Let's write down the equilibrium constant expression, which would be K equilibrium is equal to B to the power of 2 divided by A. And that whole thing is going to be equal to 4.5 times 10 to the power of 5. Now let's take a look at the possible answers. There is twice as much A as there is B in the reaction vessel. Well, that's definitely not true, because if you were to plug in, so let's say for A, you were to plug in and you were to say that your K equilibrium is equal to B squared over A. Well, let's just imagine that you have 2 moles of A, right? Because it says there's twice as much A as there is B. Well, let's just imagine you have 1 mole of B squared and then over 2 moles of A. So that would be 1/2, and that equals 0.5. That doesn't equal 4.5 to the power of 5, so that can't be true. There is more than 100 times more B than there is A in the reaction vessel. Let's try that. So let's just plug in a number. Let's just plug in 100 for B, and then we'll plug in 1 for A. So if we put 100 squared over 1, that's 10,000 divided by 1, which equals 10,000. Now it says here, which statement is true? Now it says there's more than 100 times. Our K equilibrium, right, 4.5 times 10 to the 5 is greater than 10,000. Therefore, B must be greater than 1,000, or greater than 100 times more, or there must be more than 100 times more B than A. Therefore, B is the correct answer. You can see that C is impossible, and there is twice as much B as there is A. You can do the same exercise where you plug numbers in, and you're going to end up not getting the right K equilibrium. Changing the temperature will have no effect on the equilibrium. Well, that's definitely not true. The only thing that can affect the equilibrium constant is a change in temperature. There we go. So B is the correct answer. Question number 19. The reaction shown below is at equilibrium. Use Le Chatelier's principle to predict the effect of adding ammonia gas to the equilibrium reaction mixture. If I go ahead and rewrite the reaction, so I have my nitrogen plus 3 moles of hydrogen, I write my reversible reaction arrow, and it produces 2 moles of gaseous ammonia. Now it's asking us to use Le Chatelier's principle to predict the effect of adding ammonia. Ammonia is NH3 gas. So we're going to increase the amount of ammonia gas. Now, Le Chatelier's principle states that if a system in chemical equilibrium is subjected to a disturbance, it tends to change in a way that opposes this disturbance. So if you imagine that the system is at equilibrium, if you increase the amount of ammonia, that's going to push the reaction to the left to try to diminish the amount of that ammonia. And so we're going to have an increase in the amount of nitrogen and hydrogen. Therefore, the reaction or the equilibrium position is going to shift to the left. And question number 20 says, which of the following, if changed, would change the value of the equilibrium constant of a reaction? Now, if I look at a generic reaction, if you have A in equilibrium with B, to write my equilibrium constant, it's going to be equal to B, concentration of B over the concentration of A. It says here, what's going to affect or change the value of the equilibrium constant of the reaction? Changing the concentration of the products or the concentration of the reactants is not going to affect the equilibrium constant based off of Le Chatelier's principle, because if the system is in equilibrium, it's going to shift to counteract a change in products or a change in reactants. The size of the reaction vessel is going to have no effect on the equilibrium constant. as will a catalyst. A catalyst will speed up the rate of reaction. This will affect the rate, but not the equilibrium. The only one of these that's going to affect the equilibrium constant is temperature, because a K equilibrium value is going to be a constant. K equilibrium is a constant at a constant temperature. And therefore, the only one of these things that would affect my K equilibrium would be a change in temperature.